All right. So can someone just say yes in the chat if they can hear me? Good. All right. So we're going to continue on today with this normalization theory. And right after lecture today, I will release recitation number 4, which is on this topic. And then on Thursday, we'll have another lecture where we'll continue discussing normalization theory. And it's probably a good idea to look at recitation so you kind of have, you can ask more pointed questions on Thursday. So Thursday is going to be more of a loose lecture where I take more questions and kind of are a little more fanciful. All right, so are there any questions right now before I start? Okay. So let's just review a little bit. Okay, so remember so typically the way we set these problems up in the abstract sense is we have a relation and then we have the attributes of the relation, and then we have a set of functional dependencies. So for instance, A goes to B and B goes to C, D. All right, let me just focus that a little bit. All right, so this is a functional dependency. So this basically means that if any two tuples match on A, so the value for A is, say, blue, then they have to match on the value B as well. All right. So typically this will be something like the Pershon number and then the name. So if any two tuples match on Pershon number, then they're going to match on name. That doesn't usually happen because there's only going to be one tuple with a unique Pershon number, but it would work with something. It could work with something different, like for instance, zip code to city. There might be many, many different tuples with the same zip code, and if any of them match, then it's gonna match on then they're gonna have to match also on the same city. All right, so this is elementarily, this is kind of what the functional dependencies are talking about. All right, so what we talked about last time was we talked about this issue of when you look at this, something like this, is that under these functional dependencies, like the question might be something like, what are the superkeys? Under these functional dependencies, what are the superkeys? So usually this is like an F equals this set of functional dependencies. The question is that when R is under F, what are the superkeys of R? So the thing was always that, well, all of them together, A, B, C, D, is always going to be a superkey. But in this case here, do we have any other superkeys? Can anybody mention any other superkeys? I just put it in the chat. Like for instance, maybe A. Yeah, A is a superkey. Because with A, you can then determine all the attributes of R. So A determines B, and then B determines C, and B determines D. All right. But based on the definition, this is also a superkey, right? Because with A and B, you can determine everything as well. This right here is a minimal superkey because you can't take any smaller piece of it that maintains the superkey property. This is not minimal. Therefore, this winds up becoming at least one of the candidate keys. Okay, that's a candidate key. A candidate key is a minimal superkey. All right, so then the issue of Bcnf, so then we talked about this last time, is when is something in Bcnf? So this normal form Bcnf, which we argue it has some desirable properties. A relation is in Bcnf if all the functional dependencies, the relation under the functional dependencies F is in Bcnf if for all of the functional dependencies, the left-hand side is a superkey. All right, so is A a superkey? Yes. Is B a superkey? No. Therefore, this is not under Bcnf, right? Now, to make this under Bcnf, this is the violating functional dependency, is this one. So to make this, to decompose this to something that is in Bcnf, what we wind up doing is we split by this, which will give us then R1 equals, R1, and then we take the all the attributes in the functional dependency, B, C, D, and R2 is going to wind up being, it's going to wind up being basically getting rid of the CD. So it's going to wind up being ABCD minus CD. So it's going to wind up being AB. Okay. Sorry. Okay. So that right there is it. Now is this now relative to these functional dependencies, is this in Bcnf? And the answer is yes, because first of all, this functional dependency here only lives in this relation here, and in this is B is B the superkey of this relation? Yes, it is, because with B you can determine everything else. Therefore, that checks out. That's fine. And then likewise with AB, we have is A a superkey of this? Yes, it is. Okay, so this winds up being a Bcnf decomposition. All right. And so what the theory tells us, of course, is that we don't, if we had the choice between defining this table here in our database and defining this table here in our database, we would much prefer to define it this way. Okay, there's a lot better properties in terms of minimizing insertion, deletion, and update anomalies. Okay, right. So that was just kind of the quick review of what we talked about before. Now, there is the question of this, and that is that if I give you a set of functional dependencies, so if I give you a set of functional dependencies, so for instance, I will give you the functional dependencies A, B, B, C. So if F equals that, do these functional dependencies here, this set of functional dependencies here, do they mean that this also holds? Okay, so this right here is semantic entailment. So do the functional dependencies, these functional dependencies here, always mean that this also holds? This functional dependency here also holds? The answer is yes, because this is a transitivity rule. All right. So a lot of times what happens is you're given a set of functional dependencies, and then what you want to do, so I can just kind of write these things down willy-nilly. I'd say something like F equals A goes to B, then let's see, B goes to C, D, okay? And I want to, just to make it kind of curious here, let's make it that C goes to B, A. All right, so this, I mean, this probably corresponds to something in the real world. Okay, so there's a set of functional dependencies that we were given, that's a B. Okay, now so this right here, what this determines, let me just add something else in here. A goes to B, B goes to C, and let me just add this in here also. A goes to D. All right, so this right here is a set of functional dependencies. All right, so let's just denote that as F. And there's a set, right? Now there's a larger set, which is called F plus or F closure. All right. So the idea is that from these set of functional dependencies here, there's a whole set of additional functional dependencies that can be implied from this initial set here. All right. And that's denoted as this F closure. All right. Likewise, there's something else. There may be a subset, I'll call this little F prime, which is a minimal basis. All right. So if we take, let's look at some of the definitions. So we have some definitions here. We have a minimal basis and we have a closure. So it's always relative to a set of functional dependencies. So we can talk about the closure of F, which is this big F plus, or we can talk about the minimal basis of F, which is this little F prime here. Okay. Now in all cases, if I take what the definition tells us here is this. So let's get a definition of what the minimal basis is. A minimal basis is this. Basically, what we do is if we take the set F prime and then we close it, that's going to equal, I'd rather make this a double equal, F closed, which of course equals this F closure. Okay, so let me just circle that so we see all that together. All right, so this is a closure operator. So what this closure operator says, it says take a set of functional dependencies and from them generate all the functional dependencies that follow. And we focus here on the non-trivial functional dependencies. So we assume in this case that in all cases, these are non-trivial functional dependencies. So we will not even consider functional dependencies of the form x goes to y, where y is a subset of x. Okay, these are trivial, so we're not even going to consider those. We're only going to consider the non-trivial functional dependencies, the ones that actually say something. All right, so again, we have the minimal. If I give you a set of f, then we have the minimal basis, and then we also have just the set itself that's closed, that draws out all the functional dependencies that follow from these, and then of course we have that set itself, the closure. But all these are going to equal each other. That's the definition. So the minimal basis is kind of the most succinct way to write the set of functional dependencies so that it's equivalent to the original set via closure. Does that make sense to people? I hope. All right. This is not unique, by the way. So there could be multiple minimal bases. Given a set of functional dependencies, there could be unique solutions. There's not unique solutions to it. So there can be multiple solutions that are all different. All right. So now you're going to find out here, you're going to learn how one computes a closure, but of course no one wants to do this because your hand will get tired. And you'll learn how to calculate the minimal basis. All right. So these are going to be kind of important things. So given a set of functional dependencies, then a lot of times you'll be asking, what's the closure and what's the minimal basis? Okay, so let's start with closure. So closure basically just means, so closure of a set of functional dependencies is just these rules applied to fixed point. All right, think of it this way. If I have a set of attributes in a relation, then how many non-trivial functional dependencies are there? So if I have n attributes, how many non-trivial functional dependencies are there? It's a big number, because it's definitely going to be exponential number of attributes in the relation, but it is finite, right? It's finite. Okay, so in other words, as you apply these types of rules, you're going to wind up getting to a point where you generate no additional functional dependencies. So Armstrong's axioms is a minimal set. So you need all of these. These are all necessary to do the fixed point calculation. But these are in themselves, these are sufficient to characterize the complete closure. How would you go about proving this? I mean, you would go about proving this by and people of course have proven this rigorously. And the way you do that is basically you could derive these axioms by basically looking at the logical definition of, say, reflex. This right here is just the triviality, but you need it actually in the generation if you want to reach everything. Transitivity is pretty clear, and then augmentation. So if we have z, transitivity, x goes to y and y goes to z, then x goes to z. And here's augmentation. If x goes to y, then x augmented with z goes to y augmented with z. All right. So, but anyways, you'll find that these are enough to calculate the full closure. A lot of times, what we'll do is, like, if I basically say something like this, I'll say, okay, we can use Armstrong's axioms or whatever we want, but let's just look at this. Let's look at let's just look at three attributes. So I want to keep it kind of simple here. Start over. R, A, B, C. Okay, so let's just basically say we have A, B goes to C, and then we have C goes to A. All right, so that's F. And then let's compute the closure of F. All right, so if A, B goes to C and C goes to A, then that means that A, B goes to, if we transitivity would tell us that A, B goes to A, but that's not so interesting. We're going to stick with the non-trivials. But if C, A, all right, so basically, let's see, is there anything that we get here? Is there anything that would follow from Armstrong's axioms here? Yeah, there is something. So that would be something like BC goes to BA. So we're doing we're just doing the augmentation. Let's see, is that it then? That might be, let's see, AB goes to C, C goes to A. think that does it. It'd be maybe more interesting if I put a D here, because then we'd have to do all the augmentations there. And let's see. Okay, anyway, so there's our closure. What's the minimal basis of this? So the minimal basis would be something like this. You basically, we'll talk about how we calculate minimal bases, but this is already minimal. So that you can't take away any of the functional dependencies here and then have something that's equivalent to the initial set. Okay, so there's a real trivial aspect, but again, this business of like, well, what functional dependencies fall from what, you can characterize that completely with Armstrong's axioms. Right, you can't see the waiver. Sorry about that. Okay. So now you can see the whole paper, right? I mean, I'm assuming, or maybe not. Let's see here. Okay. All right, I'll be a little careful with that. I just wonder why does BC go to BA? Yes, let's do that right here. So why do we get BC goes to BA? All right. The reason why is because of the augmentation rule here, right? Because if X goes to Y, that is C goes to A, then we can augment both the left and the right-hand side with, in this case, so we have C goes to A. Maybe if I wrote it this way, C, if I just match exactly the augmentation rule, C, B goes to A, B, right? So now, because I've augmented B on both sides. So I hope that's clear. Is BC the same as C? Yes, the order does not matter. These are sets. Okay, so that's important. I mean, normally, I mean, what you want to do is you want to just kind of to respect the lexicographical order of the labels you're using. I mean, sometimes you'll find yourself doing that, but no, the order is irrelevant in the right-hand side. Okay. All right, so I hope that's all clear to people. We'll return back to Armstrong's axioms, but these, the thing is that if you say something like, I mean, you can, well, let's see here. I mean, I don't want to belabor the point here too much, but I'll put the stuff to the side because we might want to come back to this. But again, reflexivity, augmentation, and transitivity. Okay, that will do it right there. Okay, so I think we've kind of covered this. So given a set of functional dependencies F, and I'll make it with a little squiggle there, we can talk about the closure, and then we can talk about the closure of an attribute set also under F. So the closure of an attribute set actually is a lot of times the way you want to look at it. So what you want to say is, I mean, we've been kind of doing this implicitly. So when you guys were doing the calculations of of candidate keys and super keys, you were actually doing this implicitly. You were using well, mostly transitivity, I imagine, yeah, you were using that to calculate what the closure of a single attribute is or an attribute set rather, under a set of functional dependencies. There's a key thing here of projecting over R, which I kind of mentioned, but let's give it a little bit more of a specific treatment here. The closure, okay, so the closure. So if I'm doing this, let's say that I have A goes to B, and I have, A goes to B and B goes to C. Okay, so this is my set of functional dependencies. Okay, now let's say I have a relation R, A, C. So my question to people is that, does this set of functional dependencies here, do they impose anything? Or, I mean, first of all, this functional dependency right here, does he live? Okay, we're gonna project this functional dependency over this relation. But when we do that, it gives us basically it says no. It gives us a reject because B doesn't even live in here, right? So the way I say it is that this functional dependency here, A goes to B, does not have a happy home inside of this relation. All right, it doesn't fit. It does not project over this relation. Likewise, B goes to C. When I try to project that over R here, it doesn't fit either. Okay. But if I look at the closure, so now what's the closure? Let's compute the closure of F. So let's basically do, what's F closure? Does anybody, is there any, tell me, I mean, it's F, so I'll just basically say it equals F union. Okay, now, please, somebody in the comments or in the chat, please, someone type in, yes, very good, A goes to C. So really, when we're talking about this set of functions, so the meaning behind, when somebody writes this down, when someone scratches this down, first of all, when someone scratches this down, you say, what are you talking about, A and B and B and C? Okay, no one writes this down in the real world, but what they do write down in the real world is something like, well, the time determines the room determines the professor, etc. Okay, so these are always, the A and B, they're always related to something for real. Okay, but when you write this down, you're not just writing this down. Well, you're writing this down, right? But what the meaning is, what the actual implication of what you're writing down is, always has to be the closure. All right. So that equals A goes to C. All right. So it's like you make the statements, but there's a whole bunch of other statements that follow from that by definition, and A goes to C is one of them. So in this case here, what we do is when we consider, this relation here, we consider the functional dependencies that apply over it, we always have to consider that relative to the closure. All right. Now, when we do that, does A go to C? When we project that over R, does A go to C have a happy home inside of R? Does it live inside of R? Yes. Okay, so it projects. So what we can say is we can basically say this is the key right there actually of that relation. Okay, so the idea of projections is basically just taking a functional dependency and just determining, does it have a happy home inside of a particular relation? Okay. So that's an F, a functional dependency being projected over a relation. We talked about the closure. Now the closure is a set of attributes. So if I have this, so if I have A goes to B, B goes to C, and then I have E goes to F, let's just add that out, then the question might be something like this. All right, what is the closure of A? Does anybody have an idea what the closure of A is? It equals, now this is a little bit of a trick question. I want literally what is in here. What is the closure of A? What should I write? I mean, it's not I shouldn't say trick question, but I'm saying that I've seen people get this wrong before, believe it or not. So if I give A, what other attributes can I determine? It's going to be an attribute set. I'm doing it using these functional dependencies up here. I'm going to basically run the closure of this attribute under those set of functional dependencies. So it's going to be a set of attributes that they're going to come out. And then I'm asking, which ones are they? And I'm watching the chat. Aha, so one person says BC, and I say, no, that's not true. It's close, but not quite. So what needs to also be in here? It's the closure. It's kind of more mathematical. I mean, yes, exactly. So they got it right now. So it's A, B, C. So it's kind of, it's one of those silly things. But the thing is that, we got to keep things tight here. So, all right. So someone said EF, but no, that won't be. That won't be in the closure. But let's do another one here. What is the closure of AE? All right. So please now, what is going to be the closure of AE? Yes, we got it right. So A, B, C, D. Huh? No. Sorry about that. Actually, they got it right. I got it wrong. Because I'm just so used to having it, there's no D. All right. So good. All right. So now, all right. So that should be, so it looks like we have that kind of taken care of. Let me just I just dirtied down the backside of Armstrong's axioms. I got to make sure I have lots of paper ready to go here. Unfortunately, I've gotten a little bit of a shortage of paper these days. Anyways. All right, so, okay, so good. So projections and closure. So I hope that people understand what those mean. All right. Okay, so we covered this before. The keys of a relations. So the super key, of course, is, so, but now we have a little bit more. We can talk about we can talk basically a little bit more formally, I suppose. A super key then will now wind up being something, well, we say, it's a set of, super keys is a set of attributes. All right, so it's a set of attributes X where X closure is a subset of closure. Oh, so much about closure. Okay, under F is the implication here, where F closure is a subset of let's say Z for R Z under F, something like that. So the superkey. X is a superkey. X such that where the closure under F is a subset of Z for R Z. Okay, so then X is a superkey of R. Is that clear? More or less? So this is just kind of off the top of my head, how I'm kind of just scratching it out here. But this gives us a little bit more formal. I mean, if you want to do this formally, you'd want to kind of be a little more careful about it. But I hope you get the sense that now we have at least some formal way of talking about what really is a superkey. And then a candidate key is just simply something that has a superkey. It's a set of attributes that have the superkey property, but no subset of that set of attributes has a superkey property. Right? Okay. All right, we've done Bcnf, and it was mostly the issue was that it was a splitting rule here. When we come across a functional dependency, X goes to Y, where this is not a superkey of the relation, then we replace it by two subrelations, one being X union Y, and the other one being the original R, set of R attributes R. This is kind of a little bit of abusive notation here. Let's call that Z or something, where the right-hand side is not included, but X is retained. Okay, so you do these splitting, right? So you start out with something, and then you basically just do the splits. And at every point in the split, you're basically taking your original F, you're doing a closure over it, and you're basically just determining what of that projects over any of these subrelations. And then that's how you determine the superkeys, and that's how you determine the, well, let's see, is that right? Not quite right. Yeah, it is actually, because you're doing the closure here. Yeah, so and if you do it that way, what you're doing is you're determining all the, you determine all the superkeys based on that. And then if it's still not a Bcnf, you have to further split it. Okay, so I hope that that's kind of clear. So, all right, now we come to something called third normal form. Okay, so the idea then is behind that, if you do Bcnf, you can wind up doing that. So let's do this one here just to kind of show. Okay, AB goes to C, and C goes to B, and we're just talking about the relation A, B, C. Okay. Is AB a superkey of this relation? Can I please see? Is anybody? Yes, good. All right, so that's fine, no problem. If it was just this, it's in Bcnf. Now here, is C a superkey of this relation? No, it isn't. Okay. Therefore, we're going to have to split based on this. So what we're going to split it into is we're going to split it into R1, which is going to be the X in union Y. So what's R1 going to be? What are the attributes in R1 going to be? We're splitting this thing. Because this is a violator, we're going to split this. So what are the CB? Okay. And then what are the attributes in R2? AB. You guys got it. All right. So now we have this original set of functional dependencies. AB goes, okay, C, okay, so there's F, but let's just do, if we want to do F closure, what's F closure? Is there anything additionally in it? Is there any additional rule if I'm going to do F closure? Any additional rule? What about that augmentation rule maybe? I don't know. Is there any additional, the augmentation axiom might be able to drive a new rule maybe? I don't know. Is there another rule? Is there anything else here? No, A goes to B is not in there. There, I think there's something right there. AC goes to AB. That's right. So there's the augment. So you know, it's not, we're not going to use it, but there it is. Okay. Anyways, we take this whole thing. So that's F closure, right? And then we project that over R1 here. Okay, we're going to project this whole set. There's only 1, 2, 3 of them. We're going to project that over R1. What functional dependencies do we get out of that when we project the full closure over R1? Which functional dependencies are going to apply to R1? Waiting on chat. I'm waiting on chat. C goes to B. Very good. Okay, now, what about this? What about A goes to B? I mean, we know, by the way, this is in Bcnf, right? Well, we'll determine that. Okay. Well, C is a super key of this relation, so we're fine, right? Okay, so that's in Bcnf, no problem. A, B here. So take all this right here, this whole thing. Which functional dependencies project and have a happy home inside of R2? Any? All right, well, none. Okay, it's the empty set. All right, so, all right, well, all right, so if we take all the functional dependencies that project over, that have happy homes inside of relations, then we only get C goes to B, right? Let's take that set, let's do a closure over that, and does that equal the original F closure? Sorry about that. So this is the original F closure here, all those. Does that equal the closure of C goes to B? I mean, you might think, well, duh, it doesn't. Of course not. So, and the reason why it does not, because if I just take CB, I'm going to use Armstrong's axioms to try to derive any additional functional dependencies. By the way, can I use Armstrong's axioms to derive any further functional dependencies here? Actually, I can. This closure here would actually also equal AC, AB, right? Because it's the augmentation rule. All right, so that's what this is going to equal. It's going to be equal. C goes to B and AC goes to AB, right? This right here, though, already equaled AB goes to C and C goes to B and AC goes to B. So they are not equal, right? They're not equal. So this poor functional dependency was somehow lost, all right? So when we took this relation here, and this is the simplest relation in which this is the case, but there are, you know, infinite number of relations in which it's the case, but this is the absolute simplest. When we take this right here and we break it down to Bcnf, we can do it. We can break, this isn't Bcnf, but we've lost a dependency. So it's not dependency preserving, all right? So that can be a problem because you're going to have additional triggers or something weird that's going to have to try to enforce this AB goes to C. You're going to have to try to do that when you break things down to this right here. All right. So, well, anyways, there's another option. And the other option is to back off. Because the thing is, I mean, these functional dependencies that we elicited from people, they're important, actually. They're very important because these are the rules of the domain. If we don't maintain these, if our system's not governed by these, then we're going to be losing some key modeling aspect of the domain. So we really want to maintain these. We want to preserve the dependencies. But unfortunately, or fortunately, or just the way it is, it's a fact, you know. So, you know, it's not unfortunate, it just is, right? But the fact is that you cannot always guarantee that from Bcnf. Okay, so I've got a question here. Oh, sorry. Yeah, sorry, move the paper down a little bit or up a little bit. Oh, I'm sorry. Yeah. I'm sorry about that. Yeah, so anyways, what I was showing here is I was showing that I gotta, oh, I'll do it in a second. All right. Maybe now. Put it off. It's a little better. All right. Anyways, always everything's a trade-off. When I did the closure of just CB, because remember, CB was the only the only functional dependency that was able to survive by being projected down to here. If we do the closure of that, we just get, by the augmentation rule, all we get in the closure is C goes to B plus this augmentation, right? And then that does not equal the original set. So so it's not dependency preserving. Okay, shouldn't relation R2 be AC? No, not in BCNF. Because in BCNF, what happened here was we had, this is the one, C goes to B was the one we were driving. This did not maintain, did not meet BCNF. This is not a super key. So you take basically X union Y, this union that, which is CB, right? And then you take the full set ABC minus B, which equals, if I'm not mistaken, sorry. Which is equal to AC, which you're right. So you're right. I apologize. How did I do that? Anyways, I did what I did. I had AB there. All right, sorry about that. CB, fine. ABC minus B is equal to AC. Good eye there. Sorry about that, everybody. But everything else I was saying is correct, except for that, I guess. Does that change anything? No, because CB is still the only place it lives. But it does change something in the sense that yeah, you want that. Otherwise, what would happen if I had done that? Yeah, would that have caused that would have most likely generated something that was lossy. All right, so that would have been a very, very bad decomposition. So thank you very much for seeing that. All right, okay, made a mistake. All right, okay, so where were we? All right, so anyways, in this very simple example, we were not able to preserve all of our dependencies. This one got booted. All right, so the issue now is that we want to back off a little bit to a weaker normal form, which is called third normal form, which actually allows for us to do, we can always guarantee that we will preserve our dependencies. So if we want to preserve our dependencies, we can go to 3NF, and it has a little bit less stringency than BCNF, and that's what we cover here. So, you know, you might say, well, does this ever happen in the real world? Sure. This is exactly this form here. A, B goes to C, C goes to B. Street address plus city determines the zip code. And likewise, a zip code determines a city. Okay. And then this might be another example here. So that, you know, you can, A equals time, you know, like the time of day or whatever. And then B is the professor, and that determines the course. And then also the course determines, you know, if there's only one professor per course, the course determines the professor. Okay. So in this case here, so in this case here, we might say, what are the two candidate keys? Let's say candidate keys. The two candidate keys would be AB and AC, right? Those are the two candidate keys. All right. This of course is in violation of BCNF, so we did a decomposition, but that's not so great. So all right, so let's get the third normal form here. So what is third normal form as a relaxation, or not a relaxation, but little bit less stringent version of BCNF? So third normal form. Something is in third normal form. Basically, we need one little thing right here for us to kind of define what third normal form is. We have the notion of an attribute being prime. Okay, so one sec. All right. I think maybe what we'll do is instead of let's just see here. Let's just see what we can do about this right here. First of all, an attribute is prime if it is. Let's start out with what the notion of prime of an attribute being prime is. an attribute is prime if it is a member of any candidate key. All right. So what were our candidate keys here? In this really simple example here, we have two candidate keys, AB and AC. All right. So let's just, if I'm starting over again, if I said this, if I say A, B, C, and I'll say A, B goes to C, and I say C goes to B. Now let's just kind of get it back so we just repeat again here. What are the super keys of this? Give me a super key of this relation. Okay, well, ABC, right? Give me more. Somebody tell, what are all the super keys of this relation given these definitions here? What are all the super keys? Okay, super keys. ABC is one, right? Are there any other super keys? AB. Any others? AC. Yeah. Any others? No. No other ones. Okay, so that's it. Those are the super keys. Now, of these, which ones are minimal? So what are the candidate keys? Right? Those are the candidate keys, A, B, and AC, because you can't take anything away from them. All right. Now, I told you that an attribute is prime if it is a member of a candidate key. All right. So which attributes are prime here? Yep, A, B, and C. A, B, and C. They're all prime. Okay, so keep that in mind. Okay, so they're all prime. So the way it works here now is basically it says that, I'm just going to give you some kind of intuition here. This is not in Bcnf, right? Because that's not a super key. So for 3NF, first of all, in 3NF, we look at all the functional dependencies as something of this following form. When I say A here, I don't mean literally A, I mean just any attribute, okay? Maybe I could do a little extra squiggly to mean that or something. It's kind of a pretty ugly way of doing it there. Script A or something. Yeah, let me do script A. All right, that's my script A. I'm not used to it. I'm too used to a computer these days. All right, so basically that just means any arbitrary attribute, any arbitrary set of attributes. So you can always take a set of functional dependencies and put them into a form. You can break them up into a form where you can do this. We'll talk about that in a little bit in a second here, but you can always do that. But basically what 3NF, the definition is, it says basically, and these are already in that form, by the way, because what it said, because this right here is a single attribute, that's a single attribute. So this is already in that form. And we'll get to that form in a little bit, next hour. But basically what it's going to say, it's going to say, all right, for 3NF, either X is a super key. All right. Now, when I say either X is a super key, so right now what that shows is it shows if anything is in Bcnf, it's going to be in 3NF by definition, because there's an or here, right? And this is the condition for Bcnf, that X is a super key, right? So if anything's in Bcnf, it's also going to be in 3NF. But 3NF also says or A is prime. Okay, so let's apply this here. So we have condition 1 and we have condition 2. All right, and let's look at this right here. AB goes to C. Now, is AB, for this relation here, in these functional dependency here, is AB, that is X here, the AB, is that a super key? Yeah, AB is a super key, right? So it's fine. So it checks off. Let's give that a green on the first. I'm meeting this condition of 3NF. All right. Now let's go on to this one here. Is C a super key? And I'm waiting on the chat. No. All right. But is B prime? Yes. Therefore, this is already in 3NF. Okay. So this 3NF is able, now, that also means that it's going to be able to preserve these dependencies. All right. So we don't need to like do anything with this. This is already in 3NF. Okay. So what we're going to show in next hour is we're going to show, given a set of functional dependencies, how do we actually do the 3NF decomposition? So what's going to be good about that is we're guaranteeing that we're going to respect all of our functional dependencies. They're all going to be within, they're all going to have a happy home inside one of the relations. So we're going to do a algorithm, which is called the synthesis algorithm, which is able to have it so that we compute 3NF, and we do it so that it preserves all the dependencies. Okay, so let's get back at 11:15 and we'll resume with 3NF synthesis. Okay, all right. And you can put any questions in the chat. I'll pause the record now. Okay, I resumed recording here, and I assume that everybody can hear me. Please, someone confirm that. I'm sure. I'll just, yes, good. I see, yes. Okay, good. So people can hear me. All right. So now let's move on to actually doing the synthesis algorithm. Again, we can always construct a decomposition into 3NF relations. Okay, so we can always do it. And then, okay, lossless. We'll talk about that a little bit in passing in a second. But both are top-down, that, you know, the tree, Bcnf tree decomposition algorithm, the top-down one, and also the one we're going to show here. They're always lossless. Okay, so they don't introduce spurious tuples. So in other words, like just based on the first lecture, when you take the relation apart, you can always kind of put it back together again. When you take apart the universal relation, when you take it apart into constituent or decompose it into relations, you can always rejoin it back together again and not lose any information. It's hard to imagine a useful case where that wouldn't be the case. Okay, so they're always going to be that. We're not going to prove that, but there are proofs for it. I mean, if I had a lot of time, we could go through that, but we don't have that much time. But we can always preserve the dependencies, and that's the important part. Okay, so the thing is that the first thing we need, though, in doing this is we need what's called the minimal basis, right? So remember when I showed the functional dependencies, I showed there was the closure, and then there was that notion of this minimal basis. We're going to need to be able to compute those minimal bases for this synthesis algorithm. Okay, so the basic steps, just to kind of start off here, is the right-hand sides are single attributes. So we're going to convert all of the functional dependencies into I don't want to say normal form. I don't want to say that. We want to put them into a form, however, where they have single attributes on the right-hand sides. And then once we do that, we're then going to actually go and make sure that no functional dependencies are redundant. Or that by doing that, we'll construct our minimal basis. And then also no attribute can be removed from the left-hand side. This gets a little trickier, but I'll just mention this in passing. But strictly speaking, to get a minimal basis, you need to also basically, you need to consider whether or not you can reduce the size of the left-hand sides as well. All right, so let's just get into an example, because I think that'll make things a lot clearer. Let's assume that we have the following table. We have A, B, C, D, E, F, A, B, C, D, E, F, G. Right. And then we have B goes to D, F, G. And we have C goes to E. And we have F goes to G. All right. So we came up with all these, and then we from the domain expert or somebody else, we've elicited these as the functional dependencies that govern the domain. Right. And next on Thursday, we're going to talk a little bit about how you actually do this and how this is actually kind of interesting practice about how you get these kind of statements out from people who understand the domain. Anyways, all right. So then we have that. Now the first step of this algorithm is is we want to put the right-hand sides into single attributes. Okay. And by the way, just to kind of like, for people to, 1 second. I have a question here. If it read y is prime, if each element of y is part of some candidate key. Yes, this is a question. So what's prime is an attribute. So I think there might be a typo. I'll have to go back and refine that. But basically, y is prime if it is part of some candidate key. So somebody was basically saying, they said that it read y is prime if each element of y is part of some candidate key. A much cleaner read of that, and correct, would be y is prime, y being a single attribute. Y is prime if it is part of some candidate key. And speaking of which, I would like to have people just on the side. I'm not going to do it right now, but could somebody on the side right now compute a candidate key of this relation, all right, and then put that in the chat. So I'm relying on someone to. I want somebody to generate the candidate key here. All right. So as we're doing this, I'll just assume that somebody will report back with what the candidate key is in the chat, because we're going to need it later. All right. All right. So the first thing we're going to do, that's a single attribute. That's good. So, things are going to be of the form x goes to, I'll make it a script A, big script A. All right. A little doohickey there. All right. X goes to script A single attribute. This functional dependency is in that form. That one is 2. This one, however, is not. All right. So let's bust this one up and say B goes to F and B goes to G. Right? Now somebody might say, well, according to you, Michael, I mean, how do you know that? How do you know that's true? How can you do that and have it so that this set of functional dependencies is exactly equivalent to what we just had before? So how would I go about proving that? How do I know I'm not screwing anything up by doing that? Well, let's just do the kind of the simplest case of this. Of course, I need a piece of paper. I'm really running low. Let's do the simplest case. Very good. If A goes to BC, does that mean that A goes to B and A goes to C? All right. Remember, this is semantic entailment. So this is just kind of, is this the truth? Okay. Well, we have these Armstrong's axioms, and that is if and only if A, because they're Armstrong's axioms are sound and complete, A goes to BC. This is the little turnstile. So this is basically using Armstrong's axioms. A goes to B and A goes to C. So can we use Armstrong's axioms to show, so let's just, this just by symmetry, we'll just do one side of this. Does A go to BC imply, using Armstrong's axioms, that A goes to B? How will we do that? Well, let's just do it. Let's form that proof, so just so that we kind of can really kind of feel settled here. Well, let's see here. A goes to BC, sure. Now, I'm just going to, is it true under Armstrong's axioms that BC goes to B? Is that true under Armstrong's axioms? Now I got to dig this up. Where did I put them? Here, Armstrong's axioms. Where have you gone? Where have you gone? Armstrong's axioms. Ah, here we are. Reflexivity. X goes to Y when Y is a subset of X. BC goes to B. So therefore, this is coming from Armstrong's axioms, right? We have A goes to BC, that's just given. And we have BC goes to B, and therefore, using transitivity, we get A goes to B. Right? Okay, so therefore, it's because of this, we rely on the sound and completeness of Armstrong's axioms. So based on that, we know that we can split up the right-hand sides. All right, so I hope that clears things up for people, so that as we do this right here, so now I hope, based on this little thing I just did right here, and the symmetry works for A goes to C, whatever. I hope that everybody is okay with me having done, turning this from B goes to D to B goes to F, B goes to G. Is everybody cool with that? May I proceed? I'm assuming the answer is going to be yes. Yeah, good. Okay. All right. So now that we've done that, so we've done the first part. We put the right-hand side to single attributes. Very good. No functional dependency can be removed. All right. So let's see here. Now, I'm going to look at this guy right here first. Using all of these right here and Armstrong's axioms, can I derive that B goes to D? B goes to F. Doesn't look like D is on the right-hand side of anything here. So I see it cannot. I cannot use these here to derive that. Of course, the computer is stupid, right? A computer doesn't look at these things and automatically know it. So but the computer's fast, though. So it generates the whole closure out, and it finds that B goes to D is not in the closure. So, anyways, either way, this guy is going to survive the cut. Now I go to this guy right here, get rid of that, and I'm going to say that plus this, so B goes to D plus the rest of them, everything except for this right here. Can I use all of these to derive that? Again, we look at it and we say, of course not, because C is not on the left-hand side of anything here. But computers they're dumb, so they can't see that. But they take 1, 2, 3, and 4, and they do the transitive closure, and they don't find C goes to E in it. Okay, so this one survives as well. Now let's go to F goes to G. F goes to G. Well, likewise, by the same thing, we look as humans, we know that there's no way we can get F goes to G from all these other ones, but a computer's dumb, and the computer has to take this, 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 and this, do the full closure calculation, and determine that F goes to G is not inside the closure. So therefore, this one survives. B goes to F. Now, B goes to G, and then, this might happen, right? B goes to G, and but it grinds to a halt. And no, the computer takes this, 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 and this, does the full closure, and does B go to F inside that closure? No. All right, so it survives. Now, B goes to G. All right, well, it takes this full set right here, it does the closure, and B goes to F, F goes to G. And by the transitivity here, B goes to G is inside that closure. Therefore, this functional dependency is kicked to the curb. All right, so these now are a minimal basis. Right? These are a minimal basis of the set of functional dependencies. All right, so now if you wanted to, so we don't have to do this other step here. So there's another step that has to do with can you remove attributes from the left-hand side? So the thing is that all these left-hand sides are single attributes, so no, you can't. But strictly speaking, if you have more than one attribute, you have to go through the test of determining whether or not, if you remove it, do you still generate the same closure? So in other words, if you take everything and you take the functional dependency that with the can you regenerate the functional dependency with let's say that we had H here or something, right? So I would say basically, can I get rid of it? Can I get rid of H? What you would do is you basically say, well, can you regenerate everything? And actually, that would be a good example. Let me see here. Yeah, if we had the functional dependency be H here, then we could yeah, we could. No, we couldn't. Yeah, forget that example. That the idea though is that basically once you have sets here, maybe I'll explore some of this on Thursday. I'll show an example where we can do this maybe, but where it needs to happen. But anyways, so there's that little kind of extra little glitch that can happen where potentially an attribute can be removed on one of the left-hand sides. But in this case, they're all single attributes, so you can't do it. All right. Okay. So now we've done that. This is now a minimal basis, by the way. This is a minimal basis. And all right, so this is the first step. So now we have a minimal basis. That was this step right here to calculate the minimal basis. All right. So yeah, this is just a description of what I just did. All right. So, so now, maybe I'll just go through here. Now, all right. What we do here now is we take the left-hand sides, B here and C and F, and we group based on the left-hand sides. So what that means then is it means that we're going to have one group. This is group 1, right? Because we have B on the left-hand side. And then this is going to be group 2 because we have C. And this is going to be group 3 because we have F. Okay. Now from each of those, we're going to now determine relations. All right. We're going to have R1 is going to be B, D, and F. Okay, so we simply take the left-hand side, and that, of course, is going to be the key. We take the left-hand side, right, and we take all the right-hand sides and we union them together, and then we get that one relation there. And then likewise, we're going to do that for the group 2, and there's only one relation to consider, and that's C and E, right? So the C is the key, and then we have the attribute E, and then R3 is going to be F, G. All right, so based on that now, each of these functional dependencies now, we can see they have a happy home in one of these relations by definition, right? By definition, they're each having a happy home in one of these relations. Therefore, they're all being preserved. Now we have a slight problem here, and I think that someone alluded to it here in the chat here. They said, what happens to A? Good question, what happens to A? All right, remember how I asked somebody to give me the candidate key of this thing? Did anybody calculate the candidate key? I don't see it here in the chat. Did anybody? Let me see, scroll up a little bit. No. Aha, now we got one. All right, so a person did, and they did it correctly, by the way. The candidate key is, in fact, or our candidate key is A, B, C. So basically, does this contain A, B, C? No. All right, so you can basically, A is going to have to be in any candidate key, and it looks like B will have to be there as well, and likewise C. So I think this is the only candidate key. Now, the question you ask is the candidate key wholly contained within R1? No. Is it wholly contained within R2? No. Is it wholly contained with R3? No. Therefore, to make it so that everything can join, everything can be lossless, you need to add in a table that is the candidate key. All right. So that right there shows us, so that's the synthesis algorithm. So again, the first step is you take the functional dependencies and you make them so that they only have one attribute on the right-hand side. Then you go and you calculate the minimal basis by potentially getting rid of some of the functional dependencies. Then you group the left-hand sides, and then based on that, you define tables that include the left-hand sides and the union of all the right-hand sides for a group. All right, that here determined 3 tables. Then you ask yourself, finally, is a candidate key defined somewhere within these tables? All right, and if it's not, you have to add in the last table, which is a candidate key table. All right, so that is the synthesis algorithm. All right, that's how you do it. Yeah. So. Right. Okay. So just to recap here, we have just to recap the whole thing. We both our Bcnf decomposition algorithm and our 3NF synthesis algorithm always give us a losslessness, right? So we don't lose any information, but we can only be guaranteed that dependencies are preserved under the 3NF synthesis algorithm. Okay. All right. So I hope that's clear. Are there any questions about this? Any questions? In the chat? If not, we'll move on to multi-value dependencies and what's called fourth normal form. All right. Okay, I think I'm trying to think if there's anything I've missed here. I'll just say a couple things before we get to the multi-value dependencies. If you're interested, there's basically these proofs as to why things there's proofs as to using what's called the chase algorithm to prove why things stay lossless under these two different decompositions. So I say that they're lossless, but there's some kind of, it gets somewhat intricate showing that. But I would just have to, maybe if you want to, you can explore it in the textbook. But the chase algorithm is the basis to figure out why things, or how to determine if you can, basically given a decomposition, we have an algorithm that can tell us whether or not it's lossless. All right, and that's called the chase algorithm. So you basically present a decomposition. I say, is this lossless? And I have an algorithm to actually to compute that. Now we're not going to cover that in this course, and we're not going to have that in the exam. But I thought I would just mention that there is this thing called the chase algorithm through which you can determine whether or not a decomposition is lossless. All right. So multi-value dependencies. All right. So multi-value dependencies. The best thing to do here is, first of all, multi-value dependencies. Let's just look at the following example here for multi-value dependencies. Let's keep it really simple here. Okay. Let's say we have R, and what R has is it has a like, let's say, a name, and it has a color, and it has a size. Okay, name, color, and size. All right, so the name might be something like 501s, right? So like Levi's 501s or something. And they come in blue, they come in black. All right, let's just keep it that way. And then they come in two different sizes as well. So they come in, let's say, medium and large. All right, so we didn't cover that so much we didn't cover it at all, in fact, but there's this notion here, we say something like a garment. Garment? No, that doesn't come very well. Name. Color. And size. That's an entity, garment, and this is the name, this is the color, and this is the size. These are what are called multi-valued attributes. So these attributes here, the idea that a garment is going to come in several different sizes and come in several different colors. Okay, so you can see this can come from your ER diagrams. But when we look at it in terms of the tables, it kind of gets really kind of weird, actually. And the reason why 501s, yeah, the reason why it gets weird is that if we, I say 501. The reason it gets weird is if we're going to put this actually in a table, it kind of, I think somebody's coming here. It might get a little bit, it might get, let's see. So we have blue in medium, we have black in large. In fact, it's really kind of stupid, but we have to kind of present all the combinations in the table. Black and blue. So we have blue medium, black large, black medium, blue large. Okay, and then they're all 501s. All right, so already intuitively, this feels kind of stupid that we're doing this. That we're actually having a table that's defined like this. Why? I mean, why would we do this, right? I mean, that would be kind of like there has to be a better way. So our intuition looks at this and says, "Good grief! What does our intuition say? I mean, what do we say intuitively when we look at this? We say that, like, if somebody presents this as the database design, we're going to say no. What's wrong here? So let's forget about theory for a second. Let's just say, how are we going to repair this thing? I mean, this is. I mean, you know, people see the problem here. I mean, this is writing all this over. I mean, if I have if I have color, size, and then let's say I have color, size, and then I have another thing called maybe like, I don't know, like fabric types or something. It's just going to wind up being this big mess of all these combinations, all kind of redundantly. It feels kind of redundant, because what happens if somebody comes in here and they turns median here to medium, but this one stayed the same? then we have this update anomaly, right? This thing looks like junk. Something's wrong here. Something's definitely very, very wrong with this design. But what is this in Bcnf? Is this in Bcnf? What are the functional dependencies that hold over this? Are there any functional dependencies that hold over this? I haven't said any. Is name a key of this relation? Is name a key of this relation? I'm waiting for it in the chat. Name is not a key of this relation. That's right. It's not. So that's not a key. All right. So this is in Bcnf. Okay. But we would be like, it would be nice if we had some theory that told us that this is a terrible design so that we could somehow get the following instead. This is much better. Name, color, name, size. Right. This is what we want, right? We know what we want. We want to have 501 blue, 501 black, 501 large, 510 medium. This is what we want. We somehow want to have this, we want to represent the table this way rather than this way, right? That's what we want. But our theory is not telling us how to do that. It's just, it's leaving this up to kind of us just kind of using common sense. And we don't want to do that. We want to rely on theory to kind of guide us, not just kind of intuition and sense, right? Okay, so this is the motivation for multi-value dependencies. This is why we want to look at them just to kind of get a fuller or more complete picture of this whole process. This is a trivial example here. Maybe multi-value dependencies might come up in other contexts, but just for the sake of just kind of it is university class, so for the sake of just kind of interest, let's look at what's called a multi-value dependency. Now, when we look at this, I'll keep on returning back to this here. This relation here is actually under two multi-value dependencies. This is how we represent a multi-value dependency, by the way. Right? So we have one name multi-determines color and name multi-determines size. Those are the two multi-value dependencies that are governing this table. All right. Okay. Notice there's no key here. But this basically says if you give me a name, I can give you a set of colors. If you give me a name, I can give you a set of sizes. Right. That determine a set of sizes. All right. So let's see here. That's the definition. This is not the definition yet. We're going to get the we'll see that the definition is a little trickier than this, but this is the kind of the spirit, at least, of what it is. All right. So, but what is a multi-value dependency? Okay, what does a multi-value dependency say? What is it actually logically saying? What is it saying kind of at the basis of its logic? X multi-determines Y says that if two tuples of R of the relation agree on all attributes of X, then their components in Y may be swapped, and the result will be two tuples that are also in the relation. All right, so what does that mean? So I'm telling you that name determines colors here. So what it's going to say to us, if we have two tuples that agree, so for instance, we have two tuples that agree on name, any possible combination here. That means that holding the other attributes the same, we can induce two fresh tuples. So what it basically says is that it says this. Let's just say that we wind up, maybe the easiest way to do this would be this. Let's say that I also have in here 501, let's see, blue, small. All right. So this is not complete yet. This table is not complete yet. All right. So now what this means then, it means that if we pick two that match on the name here, so we're going to pick this one, and we're going to pick that one. Okay, so we pick this tuple and we pick this tuple. What it means is that inside of R, then their components in Y may be swapped, and the result will be two tuples that are also in the relation. So black and blue can get swapped, and what this would mean then is it would mean that we would get to add So it would mean that we get to add that by definition of the multi-value dependency, and then if this tuple and this tuple were in the relation, then so would be 501. Okay, now black gets swapped for blue in this tuple up here. So then we get blue and medium. And then blue gets swapped for black in this one here, 501, black, and small. Okay, and you know what will happen here is if you just kind of apply this the fixed point again, is that you're going to fill in you're going to fill in all the combinations by the definition of the multi-value dependency. Okay, so that's kind of what it is saying. That's what multi-value dependency is really logically saying, declaring what it is. Okay, so that's what it's saying. All right, now let's move on then. So that's the definition there. But so these are some examples. We've already kind of covered the example, I believe, in the case of the garment. What's important here in this example, though, which is the reason why I didn't start out with this example. But if you go to this definition here, you'll say something weird happens, or it feels like something weird happens, because what this will also do is this will also, in this case here, what we have name multi-determinants, phones and names, and beers like. What we'll see that happens here is that if you have if you have two attributes here, name determining the address, so that makes sense because you can have multiple addresses and phones, address-phone combinations, and beers liked. Actually, it's not quite the example, but what I was trying to get to is if you had something else out here, name, and then let's say something like pet's name, then this will wind up getting replicated quite a bit as well. So the multi-value dependency of name implies phones will, I see, maybe they already did that with address. So you can only have one address, but you can have multiple phones. So in the definition, what will actually wind up happening is you'll wind up duplicating all these combinations. But anyways, it's not so important to go over that quirk of it. It's just kind of where things can get confusing a little bit with multi-value. Okay, so then maybe this is the way to kind of get to this, to get more to the heart of this. All right, so every functional dependency is okay. So this is where it kind of gets a little bit trickier. So every functional dependency is actually an MVP, an MVD, a multi-value dependency. That's kind of part of a more complete set of axioms. So if you think about it, these are, when it determines something, it's determining a set. It's just a singleton set. Okay. So then there's a complementation. So it's much more complicated axioms that govern this. And one thing that's interesting is that the splitting doesn't hold over MVPs. So generally, you cannot do the splitting of well, you cannot do a splitting of the left-hand side. Generally split the right-hand side, I believe, of the MVD. So anyways, I mean, these things actually get really complicated. So they're kind of interesting theoretically. But I think for our point, what we want to do is we want to look at basically this right here. We want to basically get to this fourth normal form. So what fourth normal form is, let's just get the definition of what fourth normal form is. What fourth normal form is it's a relation is said to be in fourth normal form if whenever there's a multi-value dependency that's non-trivial, then X is a superkey. Okay, and then a non-trivial means that X is not a subset, Y is not a subset of X. and X and Y are not together all the attributes. Okay. So because there's a kind of a more extended notion of triviality for for multi-value dependencies. What this means then is the following. All right. So if whenever XB is non-trivial, okay. So let's get back to this right here. So when we look at this right here, we say that okay. Let's look at this guy right here. Is this guy in fourth normal form? Okay. Well, it has the name color. Sorry, it has name color that applies over it. That's not a trivial multi-value dependency. Okay, and it is. And then the question is name a superkey of this relation? And the answer is that name is not a superkey of this relation. So this relation is not in 4NF. All right. So there's a problem here. So what this is, again, what this is showing us that we have a theory now, because we have this definition of 4NF that basically says that whenever there's a functional dependency that's not trivial, then X has to be a superkey of the relation. Then what that allows us to say is it allows us to say, oh, there's a problem with this relation here. It is not in 4NF. Okay, it is not in 4NF. Therefore, we're not done with this yet. Okay. So remember now, if we're going to 4NF, we include this. So 4NF basically says that it also includes the definition of functional dependencies as well, because they promote up. So basically, if something is in 4NF, it will be in Bcnf as well. So it's a little bit, it's just a bit more strict than Bcnf. But what this allows us is once we're given multi-value dependencies, it allows us for the theory to complain about this this relation here. And then based on that, we just do the same thing that we did for the decomposition. We will now break this into two relations using the splitting rule. So we'll get the relation XY and then the relation of Z, all the attributes, minus Y. So basically what the theory will tell us then is it tells us we have to split it into R1, I had before, name color, and R2, name size. All right, and then once we do that, and then we look at this multi-value dependency against this right here, well, this is trivial. This is because it covers all the attributes of the relation inside the multi-value dependency. This is trivial, and therefore we can say this is meeting 4NF. Right. So what I've covered here, I didn't want to get too much into the. I mean, a lot of the stuff with 4NF, it's very intricate, but it's not really that practical. But it's nice to kind of know at least that there's this theory that will allow us, given multi-value dependencies, to move into this to go through the full decomposition. Okay, so that was kind of the reason why I covered this. Okay, so you can review the slides if they say they don't know anything. So yeah, so I think that'll do it. All right, so I think that we'll probably, unless there's questions, but maybe if there are questions, I can just handle them now. But we have a lot of time to kind of explore some other aspects. What we're going to do on Thursday is I want to kind of go into maybe more of the kind of more of the softer side of this, in the sense that how do we actually elicit these kind of functional dependencies and multi-value dependencies from people? Is that useful? Is it we're going to try to contrast that with entity relationship modeling? How do they complement each other? We have these kind of these, because again, we want to look at this design issue because it's an important issue to look at in the world to get the right database design. So we're going to try to put all this together, the entity relationship modeling plus the normalization theory, and kind of have explore kind of how they all kind of can get put together to at least help us somewhat with our designs. So are there any other questions now? Just put them in the chat. Okay. All right. Well, with that, I will see you all on Thursday, and I will release recitation number 4. Well, essentially right now, right after class. I'll have to kind of touch it up a little bit and then release it. And so I imagine also on Thursday, people might have kind of questions that are going to relate to that a little bit. So Okay, great. See you all